In this section, we will understand Bayes theorem, which forms the foundation of various artificial intelligence and machine learning algorithms, as well as Kalman filter and Bayesian filters. Bayesian theorem is a fundamental concept in probability theory that describes how to update the probability of a hypothesis based on availability of new evidence or new data. It is particularly useful in situations where we need to revise our beliefs in light of new data or new evidences. The Bayes formula is shown on the screen. It has 4 components: prior, marginalization, or it's also called as evidence. Prior is also known as belief, and we have likelihood and posterior probability. So these are the 4 components as given in Bayes formula. So initially we start with a belief called prior. Prior is the probability of occurrence of event A. So it is the probability of event A occurring on its own, and prior is what we believe about something before we get new information or new data. So it's our initial estimate of event A. Now the second part is event B, and in data science domain, event B is nothing but availability of new data point or new evidence or new measurement. So PB is the probability of event B occurring on its own, and this is called the marginal likelihood or the evidence. It is the total probability of seeing the new data under all possible scenarios of A. It helps normalize our calculations so that the updated belief, that is this posterior, is a proper probability distribution, and it has a area under the curve which is equal to 1. So you can see this denominator as a scaling factor for this numerator, and I'll talk more about it in the later slides. Coming to likelihood, this is B given A, that is the probability of event B occurring given that event A has occurred. Likelihood is how likely the new data is given our initial belief. So our initial belief was this probability of A occurring on its own. After that, we received a data, the evidence, that is B, and now we are calculating what is the probability of seeing such data provided event A has already occurred. That's what is known as likelihood. So I'll once again clarify that likelihood is how likely the new data is given our initial belief. It is about how probable the new measurement is if our initial belief is correct. So then we have our numerator, we have our denominator, and we calculate these probabilities, and what we finally get is called posterior. And this is the outcome. This is the updated belief. So before data became available, our belief was P of A. And once the data has become available, we have updated this belief, that is prior, to posterior. By using Bayes formula, we can continuously update our estimates with the new information, leading to more accurate and reliable predictions over time. Let's examine it further with some real-life examples. In this first example, we'll take a case of medical diagnosis. Imagine you go to the doctor for a routine checkup, and the doctor suggests a test for a very rare disease. This disease is quite rare, affecting only 1% of the population. The test, however, is not perfect. It has false positive and true positive rates. So 99% chance of correctly identifying the disease if you have it, which means this is a true positive rate of the test, and 5% chance of indicating that you have the disease when you actually don't have it. So this is the false probability or false positive rate. Now the problem that is required to solve is that you take the test and the results come back positive. So given this data that your test report is positive, what is the probability that you actually have this disease? And in scenarios like this, Bayes formula works pretty fine. So we can immediately write all the priors and likelihoods and calculate the posterior. So our prior is, that is before this test, we know that it's a very rare disease and it affects only 1% of the population. So without conducting any test, a person randomly picked up from this population will have only 1% chance to have this disease. So this PD is our prior, and if we subtract this by 1, so we will get a probability of not having this disease. This is the prior probability of not having the disease, that is 0.99. Then we have two more probabilities, that is the first one is true positive rate and the second one is false positive. So the first one is given that somebody has this disease, how effectively the test works. It is working with 99% accuracy, so this probability is 0.99. And in case if the person does not have disease, still this test gives you positive results, which is false positive, so that is 5% probability. Now using this data so far, we can calculate the probability of the evidence. That is, what is the probability of getting a positive test report under all possible scenarios. So this is captured by the third formula here, which is giving the probability of the evidence. And lastly, we use the Bayes formula to calculate the probability of actually having the disease, that is this one, when you have tested positive. So it is calculated by plugging these numbers. So this is the likelihood, this is the prior, and this is the evidence. And now you can see that in spite of the fact that you have tested positive, there's only 16.6% chance that you actually have this disease. So this is how you update your belief about something once you are given new data or new evidences. Let's take another example, this time a spam email detector filter. Consider an email filter that is designed to detect spam emails. The filter works with the following probabilities. Probability that any given email is a spam, this is 20%. So this automatically becomes our prior. Then the probability that the filter correctly identifies a spam email is 95%, which is the true positive. And the probability that filter incorrectly marks a non-spam email as spam is 10%, which is false positive. And now, based on this data, we have to solve a problem. And the problem statement is that an email is marked as spam by this particular filter. Given that this email has been marked as spam, what is the probability that this email is actually spam? This is what is the problem statement. And here again, we use Bayes formula to calculate the posterior, which is given that the filter has detected a positive spam, given that data, how likely is that this email is actually a spam? So all the probabilities are plugged in here. So our prior is PS, which is this 20% before any filter action takes place. After that filter action takes place and filter is not working properly, it has got errors of its own as shown on the screen. It has a true positive rate of 95% and it has a false positive rate of 10%. So we calculate the denominator of the Bayes formula, which is nothing but evidence, using this formula. And it turns out that it is 0.27. And then we plug all these numbers back into Bayes formula. So the first term, the green term, is nothing but it is a likelihood, which is coming from the true positive rate. And PS is the prior, which has come from here. And we have calculated P positive, that is the probability of the evidence as 0.27, which we will plug it here. And when we plug these numbers, we get, the problem that we are trying to solve was that given that filter has detected a positive spam, has declared a mail as positive as a spam, what is the true probability of this mail being an actual spam? So once we have obtained the result of this filter, we have changed our belief from 20% to almost 70%. And this is how we update our probabilities and belief once the new set of data becomes available to us. In the third and the last example, we'll take the case of a car position tracker through a radar. And we will, so far we have just used discrete probabilities. But in this case, since the position variable is a continuous variable, so we will be not be using discrete probabilities, but we'll be using probability density functions. So Bayes theorem can also be applied to continuous probability density functions. Let's consider an example of tracking the position of a car moving along a straight road using radar measurement. So we have a car here. It is moving from left to right, and a radar is trying to track the position of the car. So it's a one-dimension motion for the ease of demo. Now imagine we are using a radar to track the position of a car along a straight road. The radar provides noisy measurements of the car's position at regular intervals. Our goal is to estimate the true position of the car given these noisy measurements. So the whole scenario can be depicted here. So we start here. We have no idea about where our car is. Basically, we are looking at time t0 or t0. And at this point of time, we make an educated guess about the position of the car. And this is exactly what we call as a prior. So this is what is our prior. And based on that, we are now trying to predict the future positions of this car. So once the prior becomes available to us, and it's a Gaussian probability distribution, as you can see, we get a reading from the radar. A new measurement becomes available to us, and this measurement itself is noisy. It is not giving the perfect information regarding the position of the cars, and this is shown by this brown Gaussian distribution. And now we have to incorporate this additional piece of information to update our prior. So this is done using a Bayesian formula. And after update, we get a posterior probability, which is much sharper, and it is having less variance and less standard deviation, which means our uncertainty in the system is reducing. Uncertainty in the position of the car is reducing because of the data that has come from the radar. And we update our belief, and we, in a cyclical fashion, we continue to do this operation again and again for all the future positions of the car. So as you can see, Px is the prior, this one. And it is Gaussian distributed with mean mu naught and sigma standard deviation as sigma naught. So we can write an equation like this. This is the prior. Then we have likelihood. And what is the likelihood? Likelihood is once the radar measurement becomes available, how likely are we, how likely is this radar measurement given that the car is at position X, so which is depicted by this orange curve. And it is again a Gaussian distribution. So it is centered around the mean of the car, the position of the car, and it has a variance of sigma z, a standard deviation of sigma z. And now we are required to combine both these pieces of information. So this is likelihood and this is prior. And we are required to calculate the true position of the car given the radar measurement is available to us. And that radar measurement is a noisy one. So again, you can see that this is nothing but Bayes formula. Given the radar measurement, what is the true position of the car? And we use this. Here again, as I mentioned earlier in the previous slides, this denominator is nothing. It's quite difficult to figure out this probability. Basically, it is the probability of radar measurements under all possible scenarios. So in all practical cases, this data generally doesn't become available, and we ignore it, and we remove this equal sign to proportionality sign. We are more interested in the shape of the posterior, the parameters of those posterior probability rather than the true values. And in subsequent sections, I will demonstrate to you that this posterior probability is once again a Gaussian distribution, as you can see here. So once again, this blue is the Gaussian distribution, and it has its own mean and own sigma, which is written here. And we can demonstrate through mathematical principles that this new mean and new sigma can be calculated from these two probabilities distributions, that is likelihood as well as prior. It is nothing but multiplication of these two Gaussian distribution. And this will be demonstrated in the next section.